In mathematical analysis, asymptotic analysis is a method of describing limiting behavior. The methodology has applications across science. Examples are in applied mathematics. Asymptotic analysis is used to build numerical methods to approximate equation solutions. In computer science, in the analysis of algorithms, considering the performance of algorithms when applied to very large input datasets. The behavior of physical systems when they are very large, an example being statistical mechanics. In accident analysis, when identifying the causation of crash through count modeling with large number of crash counts in a given time and space. The simplest example, when considering a function f, is when there is a need to describe its properties as n becomes very large. Thus, if f equals n2 plus 3n, the term 3n becomes insignificant compared to n2, when n is very large. The function f is said to be asymptotically equivalent to n2 as n infinity, and this is written symbolically as f tilde n2. Definition. Formally, given functions f and g of a natural number variable n, one defines a binary relation if and only if this relation is an equivalence relation on the set of functions of n. The equivalence class of f informally consists of all functions g which are approximately equal to f in a relative sense, in the limit. Asymptotic expansion. An asymptotic expansion of a function f is in practice an expression of that function in terms of a series, the partial sums of which do not necessarily converge, but such that taking any initial partial sum provides an asymptotic formula for f. The idea is that successive terms provide an increasingly accurate description of the order of growth of f. An example is Stirling's approximation. In symbols, it means we have but also and for each fixed k. In view of the definition of the symbol, the last equation means in the little o notation, i.e. is much smaller than. The relation takes its full meaning if, which means to form an asymptotic scale. In that case, some authors may abusively write to denote the statement. One should however be careful that this is not a standard use of the symbol, and that it does not correspond to the definition given in section definition. In the present situation, this relation actually follows from combining steps k and by subtracting from one gets, i.e., in case the asymptotic expansion does not converge. For any particular value of the argument there will be a particular partial sum which provides the best approximation, and adding additional terms will decrease the accuracy. However, this optimal partial sum will usually have more terms as the argument approaches the limit value. Asymptotic expansions typically arise in the approximation of certain integrals or in the approximation of probability distributions. The famous Feynman graphs in quantum fields theory are another example of asymptotic expansions which often do not converge. Use in applied mathematics. Asymptotic analysis is a key tool for exploring the ordinary and partial differential equations which arise in the mathematical modeling of real-world phenomena. An illustrative example is the derivation of the boundary layer equations from the full Navier-Stokes equations governing fluid flow. In many cases, the asymptotic expansion is in power of a small parameter. In the boundary layer case, this is the non-dimensional ratio of the boundary layer thickness to a typical length scale of the problem. Indeed, applications of asymptotic analysis in mathematical modeling often center around a non-dimensional parameter which has been shown, or assumed, to be small through a consideration of the scales of the problem at hand. Method of dominant balance. The method of dominant balance is used to determine the asymptotic behavior of solutions to a node without fully solving it. The process is iterative, in that the result obtained by performing the method once can be used as input when the method is repeated, to obtain as many terms in the asymptotic expansion as desired. The process goes as follows. 1. Assume that the asymptotic behavior has the form. 2. Make an informed guess as to which terms in the ODE might be negligible in the limit of interest. 3. Drop these terms and solve the resulting simpler ODE. 4. Check that the solution is consistent with step 2. If this is the case, then one has the controlling factor of the asymptotic behavior, otherwise, one needs try dropping different terms in step 2. Instead, 5. Repeat the process to higher orders, relying on the above result as the leading term in the solution. Example: for arbitrary constants C and A, consider this differential equation cannot be solved exactly. However, it is useful to consider how the solutions behave for large x. It turns out that behaves like as x infinity. More rigorously, we will have not. Since we are interested in the behavior of y in the large x limit, we change variables to y equals exp, and re-express the ode in terms of s. Or where we have used the product rule and chain rule to evaluate the derivatives of y. Now suppose first that a solution to this ode satisfies as x infinity, so that as x infinity. Obtain then the dominant asymptotic behavior by setting if satisfies the above asymptotic conditions, then the above assumption is consistent. The terms we dropped will have been negligible with respect to the ones we kept. Is not a solution to the ode for ES, but it represents the dominant asymptotic behavior, which is what we are interested in. Check that this choice for is consistent. Everything is indeed consistent. Thus, the dominant asymptotic behavior of a solution to our ode has been found, by convention. The full asymptotic series is written as so. To get at least the first term of this series, we have to take a further step to see if there is a power of x out the front. We proceed by introducing a new subleading dependent variable, and then seek asymptotic solutions for c.